Good morning, folks. This is Jim Chastain with EasyPower. Welcome to the Tuesday morning refresher series. This is the first in a three-part series on data collection, and what we expect to do today is cover basically what data that does need to be collected and amplify that as much as possible. The next in the series will be next week, and we'll utilize EasyPower to show how to then develop templates for your data collection process. And then the third part in this series will actually be presentation of the capabilities of a mobile app that is designed to do data collection and facilitate that even further. The biggest advantage is that the application, the tablet-based application, will end up producing a one-line diagram file that EasyPower can then utilize. So, as you might expect, the importance of data collection can't not be overstated, because it's the value and the accuracy of the study itself is dependent upon the accuracy of the model, and that is where the data is stored. So it's important to spend some time planning, and the advantage of doing it yourself or being involved in the process yourself is that you will learn more about your system and potentially save a substantial amount of money in the process. Obviously, you want to collect any data that exists, including one-line diagrams or layouts or maintenance schedules, to make sure that you have all the system evaluated, and if necessary, do some hand sketches so that your people know what to expect as you do the plan. It's important when you think about the process of data collection that safety be in utmost in everyone's mind, especially if the system has not been analyzed before. And so frankly, it's important to spend a fair amount of time planning for that and ensuring everyone's aware of the safety issues when you're doing data collection. So plan ahead, schedule as much as possible around shutdown times. Use extreme caution when opening up covers. Look for any evidence of potential malfunction, including noise, loose connections, missing screws or bolts. As much as possible, record the nameplate on the data, and along that line, use local knowledge, people that work on the system and know the idiosyncrasies and know the configurations, the normal configurations for the system's operation. It's also important to be prepared. In this list, at the end of this presentation, I'll give several references for this material, so it's not necessary that you record all this down, but be prepared. So have your PPE ready if you have to open up a piece of live gear. Have something to write with, obviously the paper, the templates that we'll talk a little bit later, but knowing what kind of systems you're opening up, be prepared for the data that needs to be collected. Obviously flashlights, mirrors so you can reach behind and view sometimes labels that may be out of direct sight, but make sure these are non-metallic. Highly valuable is a digital camera, some kind of recording device that you can incorporate what you see and not have to go back to the piece of equipment multiple times because you didn't adequately collect all the data. All right, so the steps involve planning, which is identifying all the equipment you're going to work on, actually recording the information itself, and making sure that you've covered all aspects of the system. What we're looking for is the ability to calculate the short circuit current, so we have to look for anything that affects the impedance. What we're ultimately going to be doing is calculating a worst case arc on any bus or piece of equipment. To do that, we need the voltages, the impedance and resistance characteristics, and then any time element, anything that affects the time element, and primarily these are the protective devices that would have to open in the case of a fault. So the equipment data includes the type of type of equipment, type of enclosure, type of breaker, and if you can, from the manufacturer's data sheet or during the process of data collection, determine the gap between the conductors and that piece of equipment. That's going to be useful information. We're going to be wanting to be able to label any piece of equipment that needs to be opened up while it's hot, and to do that we need data on virtually anything upstream of that. So if the equipment has the potential to be worked on while energized, it should be assessed. And this includes branch circuits in data centers and panels, switch gears, and anything served by, in fact, in many cases, transformers that are served at 480 volts, even below 500 kVA. Frequently, and more often these days, panels and switchboards rated at 208 volts with service transformers less than 125 kVA are considered a low risk, but people still want, for accuracy's sake, that data to be recorded on their one-line diagram. So all panels and breakers and fuses should be included in this data collection process. So that data includes equipment type, voltage, MVA ratings, impedance, X over R ratios, phase connections, and as far as the voltage sources, any utility information including voltages, short circuit currents, generators, transformers, cables, transmission lines, motors. And then in very great detail, all the information on the protective devices. EasyPower tools include device libraries that can look up the manufacturer's data sheet and trip characteristics for each of the device, as long as you record the manufacturer's data type, the style of the breaker or fuse, and the ratings. It's important to know that there's some information that needs to be assessed by the data collection team themselves. This includes what type of operations or work will be done on this equipment while it's hot, and that will determine what the working distance is, at what distance the technician or electrician who will be working on the equipment while it's hot how far their body will be from a potential arc source. So this is called working distance. There's also an assessment of whether or not the breaker, the main breaker or protective device in the panel that we're looking at, can be included or it needs to be excluded in terms of arc flash calculations. We'll cover this more, and we cover this more frequently in talking about short circuit and arc flash studies, but the people that know and or collect the data have to make a determination as to whether or not the main breaker of the panel is effective in providing arc flash protection. And that really comes down to, is there a barrier between the incoming cable connections to the main breaker and the rest of the main panel or the main bus of that panel? And if there's not a barrier, then that breaker cannot be included in the calculations. Again, by talking to the local team or the maintenance group, it's important to understand all possible operating configurations of the system, including parallel feeds, cross ties, additional current sources or energy sources, standby generators, and multiple utility services. Okay, so we're going to touch on each of these types of equipment pretty much in the order of, I guess, importance or contribution to the major parameters of calculating arc flash. Obviously, utility is very important, the size of the transformer, the energy in the transformer, any protective device that has a trip time, so this would include fuses, circuit breakers, relays, and ATSs potentially. Information on switch gears, motors, panels, MCC, and cables. Cables end up being a lot more of an issue than we realize, especially in older facilities. So the utility data, frequently we have to rely on the utility companies supplying this information, and it's important to explain to them that this is for an arc flash study, so that they know what type of data that needs to be supplied. This area I show at the bottom of this slide is the way the default information is supplied into or provided into the tool at EasyPower. This data is referred to as an infinite source, and so it actually, if you utilize this by default, you will get, frankly, the best case scenario in terms of trip times, because this will be much higher current than you normally get from utility. So it's important to get the line-to-line phase, short circuit available current, the voltage, and the X over R ratio at the utility point of connection. And here's what the format of that data usually looks like. Frequently, it'll be the current level, say for instance 4.5 kiloamps, and then the X over R value, both for three-phase balanced fault and for a single line to ground fault. The tool will allow other types of formatted data if that's the way the utility company set up. Transformers is where the energy is stored in the system. And so all the information required for EasyPower is included in the nameplate, and this includes the kVA rating, the type of transformer that it is, oil-filled, dry, the configuration. In this case, this is a delta Y, and the impedance. The impedance ratio being important because it's a heavy contributor in the X over R ratio of the whole system. And again, this is virtually all this information is on the nameplate. Taking a very readable picture of the nameplate is highly desirable. So as I mentioned, we're looking for the MVA or kVA rating, the rated voltage, the impedance ratio, which is usually a Z or a percentage, the phase connections, any tap voltages if there's a tap changer, the X over R ratio in subsequent or tertiary windings if you have more than a two-winding type of transformer, the cooling class. This will indicate whether there's forced air cooling and a need for increased rating with the forced cooling on. When we get to fuses, again, they're the most widely used protective device, and so consequently they're going to be encountered most often. If you correctly identify each of the fuses by reading a label or taking a picture of it, then the trip characteristics of the device will be in the library. A good point to be made here is anytime we're looking at fuses, make sure all the phase fuses are the same, and that you don't have multiple values on each phase or different values on each phase. Again, when you get into the calculation mode or whenever a calculation is made, you utilize the worst case situation, and if you have one fuse that's out of whack, that could skew your results considerably. So you're looking for the manufacturer, the type and style, the model, the rating, and the number of fuses if there's a number of fuses in parallel. And this is pretty much how fuses look in both low voltage and in some cases high voltage applications. Circuit breaker times. High voltage breakers, a critical rating here is the opening time. Again, more and more as we go through this, you'll see time is one of the very important elements of calculating arc flash. And so that opening time may be rated in cycles or in milliseconds, and this is important to record. If there's a relay that operates that breaker, make sure you identify the ID of the relay, and the relay details are recorded separately. Frequently for circuit breakers, high voltage tiles, you're talking about manufacturer, the type, continuous rating, the nominal voltage, and then if you have the ability to do additional data, by all means collect it if it's available. Low voltage breakers are actually two different types or two different parts. One is the breaker itself, and there's ratings that need to be recorded there. But then the trip unit that causes the breaker to open can be one of several types, specifically thermomagnetic, solid state, or non-solid state, all of which your data collection people need to be familiar with the alternatives or the potential types that you have in your plant. When you're looking at molded case circuit breakers, they most often have a thermomagnetic trip, and there are some that do have adjustable solid state trips. The thermomagnetic usually has a fixed thermal and a fixed magnetic and smaller current applications. And by correctly recording the manufacturer name, type, style, and part number, the device library will have the trip characteristics and the ratings already stored. So we're looking for manufacturer, type and model, frame, continuous current rating, usually on the face of the breaker itself, the trip type, and the interrupt rating, and then the information for the trip unit description itself in terms of the rating or the trip settings. For low voltage power circuit breakers in the insulated case, again, the manufacturer, the type and model, the frame size, continuous current rating, trip type, and interrupting. And then on older breakers, there will be a dash pot type of trip, and these need to be recorded in terms of the characteristics. Solid state trips, again, these are very often a separate unit or in a separate section of the breaker panel. And you need to record the manufacturer, type and model, the frame size and sensor. And again, if these are not identifiable, if you have a piece of equipment that's so old or so corroded or so degraded, frequently people will contact our tech support group and send a picture and say, hey, this breaker's installed or this trip unit's installed on this type of breaker on this type of system, and our engineers will help triangulate what the possible alternatives are if we can't identify that specific device from the photograph. So a very useful resource if you're out there trying to sort some of this stuff out on your own. And this is what the breaker format would look like. And the front panel, sometimes fine print. Again, a fine grain digital photograph can help avoid multiple trips out to the location because you can read them directly off the photograph. And a good image of these dial settings, which are the trip settings, is important, and each of these dial settings will have a bearing on the time to quench an arc. So whether you record the symbol or whether you record the number, this is greatly advisable that the details and accuracy be as complete as possible. Switches are commonly installed at loads, and in older buildings there may not have been a protective device or a fuse installed. Make sure that you understand what your installation is, if there is a switch with a fuse, and the details on both the switch and the fuses, because if there's not an adequate localized protective device, this could be an extremely dangerous setting for an arc flash situation. Switchgears, panels, and MCCs, again, anytime there's a potential for an arc in an enclosed box or enclosed area, you actually have an amplified radiation, and generally if you're looking in or working through the only opening in that box, all the energy from the arc will be radiated out the opening, and so it amplifies the harmful effects of an arc flash. So understanding the equipment type, the orientation of the bus work or the connections vis-a-vis the person doing the work is important, and sometimes this is necessary to observe as a data collector, or it can be recorded once you look up the data sheet. If you can see that orientation, and we're talking about whether it's a vertical connection or a vertical bus or a horizontal, and what the perspective is to the operator. This needs to be reflected in your notes if you can't identify the manufacturer's part number and model number. Making notes of the cables and conductors and the numbers. Sometimes things are not as they're recorded on a one-line diagram from previous studies in terms of cables that could be added or multiple connections made, frankly, in violation of code. And on the other hand, it could be very neat, which makes life much simpler for a data collection. In any case, you need to understand, and this is an example of where any voltage connections from a main breaker, if they're not, if there's not a barrier between me trying to work on this bus and the incoming 480 volts, then I can't utilize the trip characteristics of that 480 volt panel breaker. Generators are important, even though we don't operate all the time on a generator. If we're going to be inspecting or working on equipment while the generator's in operations, then we need to have very accurate data, including the kVA rating, the voltage, the speed, the frequency, serial number, and emergency or connected information on the switchgear that connects the two. Most of this information will come off the data sheet or the test sheet for the generator, and that includes the subtransient reactants and the zero sequence reactants, all of which play an important part in the short circuit data. And again, in the information at the tail end that I use as reference material, you can get more detail on this. And most manufacturers' data sheets have the information, as I say, on each of these variables. It's relatively easy once you have the information to model that device in EasyPower. Motor data. The requirement for using the IEEE model is to evaluate the system both with and without motor contribution. It turns out when we have a fault, as the motors wind down, the field collapses and actually contributes current to that fault location. And so the size, especially motors over 50 horsepower, can be a significant contributor to any kind of fault current. So it's important to record the size, the voltage, the load amps, the speed, the frequency, the NEMA code letter, and the manufacturer's name and serial number. And again, there's certain elements in the tool that allow us to make assumptions or look up some of these values if we know some basic information about the motor itself. And so we talked about all this. This is all based upon the IEEE standards C.37010 and C.375 1979. Motor contributions will vary based upon what phase of starting the motor is in, and so there's certain rules in terms of how small a motor we need to record. The tool allows us to group motor contribution and still be able to average the X over R contribution calculations. And it's pretty straightforward in the tools once you set up a motor. The point I was making earlier is whether the larger motors we set up as an individual, very small motors, especially large numbers of them on a bus or in a panel, we can group together and get an average contribution as far as the arcing current. I mentioned earlier that cables were significant contributions to impedance calculations. EasyPower provides one of the most accurate calculations for cable impedance in the industry, and we do this by entering data to calculate the construction, not necessarily a manufacturer's part number. It is good to record the manufacturer's name, and most of this information will be on the label of the cable itself, but the conductor size, the conductor material, the length of the cable, the insulation type, and the voltage, and the type of conductor, whether it's a single core, triple core, or other, all contribute to the impedance calculations. And the more accurate this is, the better life will be as you start to develop your model. Again, the purpose of this model can be far more forward thinking than just arc flash. And again, the more accurate it is, then the more usable that model is for subsequent analysis and utilized in optimizing my system operation, which is another story altogether. So this is the data entry dialog box for the cable. The red exclamation points indicate mandatory data, but they're actually calculated once we enter the basics of the number of conductors per phase, the type of cable, the insulation, the size of the cable, and then the length. Then the tool will calculate for us based upon what type of conductor material we're using and what type of conduit that's being used. And I mentioned that there is, most of this can be retrieved from the cable itself in terms of marking. Some of the abbreviations that are used in the tools may not necessarily be straightforward as far as our familiarity. On each dialog box there is a context help button, and this will help us triangulate what the label says versus what the tool is asking for and be able to cover that gap. Bus ducts and busways are, again, similar in terms of contribution or information necessity to cables. And what we're looking for here is the manufacturer's name, ampere rating and size, and the length, and then anything that's downstream, potentially in terms of loading and protective devices. And these are called out and entered because we're looking for the impedance calculations. If you have those directly, they can be entered, or they can be calculated based upon the manufacturer's information. And then, as important as anything else, the elements that control the time of the arc, that quench the arc, are highly important when it comes to calculating arc flash. Relays are an important element in this process, and so you need to record as accurately as possible the CT ratios that are feeding the relay. Obviously you want to have these on all three phases, or if you include in ground and neutral, the multiple phases. Modern relays may have LCD displays that indicate what the trip settings are, and others may have switches or dials to set these, all of which can be recorded as you're taking your data, and then make sure you're correlating those settings to which type of protection that we're looking for. Typically a 51 or 50 refer to instantaneous overcurrent, and the specific configuration or type of protection needs to be recorded along with the set points. So in general, you're going to be looking for the CT ratio, the tap, if applicable, the manufacturer of the relay, the type, the overcurrent function, the name of, or the type of the function, the delay curves, all the dial settings, and then any intentional delay based upon the way the system's set up as opposed to instantaneous. And as you get into the tools, this will be clearer, and if you need help on any of that configuration, by all means contact tech support at EasyPower.com. I mentioned earlier that there's on the EasyPower website some very valuable resource material. One is the EasyPower Notes on Data Collection for Arc Flash. You can either download that from the website or contact sales at EasyPower.com. The other document that I highly recommend is available for download. It's called Practical Solutions to Arc Flash, and it's available on the website. Let me see what this looks like. Let me kind of show it to you. It's a 150-page book, and it goes through not only data collection, but the whole process of developing an arc flash study. And I wanted to kind of scan through the table of contents. There's a whole chapter on data collection, and included in this are templates for doing the data collection. Now next week we will be going through how to utilize the EasyPower tools to generate your own templates, and the ones that are in the book are actually more on a generic basis. So I encourage folks to contact either the website or send us an email if you got questions. Sorry I can't take online questions today due to the time element, but certainly we look forward to talking to you next week when we get into the generation of the templates themselves. Thank you all for attending, and we appreciate your support of EasyPower. Have a good day.